Welcome back to the class on electrical meters 2. In this lecture, we are going to discuss about the numericals on a EMF method of voltage regulation. A three-phase star-connected synchronous generator is rated at 1.5 megavolt amperes and 11 kilovolt. The armature effective resistance and synchronous reactance are 1.2 ohm, 25 ohm. Calculate the percentage voltage regulation at a 1.4375 megavolt amperes at 0.8 power factor lagging and 0.8 power factor leading. These are nothing but a ratings of a generator. This is the maximum power that can be withstood by the generator. This is the voltage given between the two lines of a generator. Now here we have to find out the voltage regulation. So we have to find out the per phase voltage. Because whatever the values were taken in the formula of E naught, nothing but excitation voltage, all those values are the per phase values for them. So here in the numerical it is given that star connected synchronous generator, the per phase voltage equal to 11,000 by root 3, we are getting the 6351 volts. Load current equal to, here you have given how much load we connected across the generator, that is 1.435 10 to the power of 6 divided by root 3 into line voltage, it gives the load current, that is 75.45 amperes. The effective armature resistance and synchronous reactance is prolonged. Those values you have to take directly. When the power factor cos pi equal to 0.8, the sin pi equal to 0.6, we know the excitation voltage E naught or EF equal to square root of V cos theta plus IA RA whole square plus V sin theta plus or minus IA XS whole square. V is nothing but a per phase rated voltage. Cos theta value is given 0.8. Sin theta value is 0.6. IA value becomes this one. Nothing but the load at which you have to find out the voltage regulation. RA value is given in the numerical. XS value also given in the numerical. Substitute all the values. You are getting the excitation voltage equal to 7695 volts. Now the voltage regulation equal to E naught minus V by V. Here in the denominator we have taken the rated voltage. Substitute all the values, you are getting the 23.63%. The same manner, if you want to find out the voltage regulation at a leading power factor means here you have to take the minus, plus for the lagging power factor, minus for the leading power factor. Use the same formula, but the only thing is here you take the minus, substitute all the values, we are getting the 5518 volts. Again, if you find the voltage regulation, substitute all the values, we are getting the minus 13.1%. Now, the second problem. The data obtained on a 100 kilovolt amperes 1100 volt 3-phase alternator is the DC resistance between the two lines is 6 volts, current is 10 amperes, it is also DC. The open circuit test, the field current is 12.5 amperes DC, the line voltage is 420 volts. During short circuit test, the field current is 12.5 amperes DC, the armature current is rated value. Find the voltage regulation of alternator at a 0.8 power factor. First, you have to find out the per phase voltage, that is equal to this voltage divided by the root 3, we are getting the 635.1 volt. Next, full load current, because in the short circuit test, it is given that the full load current is passes through the alternator. So, to find the full load current, this rating of alternator is nothing but a full load. So, this we have to convert it into the volt amperes divided by the root 3 VL. Finally, you are getting the 52.5 amperes. But in this numerical, the armature resistance is not given directly. They have conducted the DC test to find the armature resistance. So, the armature DC resistance equal to this voltage divided by this current, nothing but 0.3 volts. But armature winding is operating at a AC voltage. So, the AC resistance will be greater than the DC resistance. So, 1.667 into 0.3, that is equal to 0.5 volts. Next, synchronous impedance. From the definition of the synchronous impedance, it is the ratio between the open circuit voltage to the short circuit current at a constant field current. The two readings are given in the numerical at a constant field current. Those values you have to take here. This is line voltage 420 volts, that here you have to take the phase voltage divided by root 3. Because it is star connected, line current equal to phase current. Already we calculated the full load current, that is this one. You take the value here. This is equal to 4.62 ohm. Per phase synchronous reactance Xs equal to square root of Zs square minus Rs square. This is equal to square root of 4.62 square minus 0.5 square. We are getting the value 4.59 ohms. Now we are going to find out the no load voltage or the excitation voltage. We know the formula, that is square root of V cos theta plus Ia Ra whole square plus V sin theta plus or minus Ia Xs whole square, where plus for the lagging power factor, minus for the leading power factor. In the numerical it is given that the power factor is 0.8, cos pi equal to 0.8, sin pi equal to 0.6. Moreover, we have to calculate the voltage regulation at full load. So this current we have to at a full load current, that is 52.5. This voltage already calculated. This is a per phase voltage. Substitute all the values, we are getting the 820 volts. Now the percentage voltage regulation equal to E naught minus V by V, we are getting the 29.11%. In third numerical, the OCSC test results of a 3-phase star connected 1000 kVA, 1905 volts 50 Hz alternator has the following data. This is the open circuit voltage. Whatever the voltage given in the numerical, that is the line voltage. This is the short circuit current. This is the field current. If we observe the short circuit current, only as a 30 amperes of the field current, only the short circuit current is given. Find the full load voltage regulation at 0.8 power factor lagging by EMF method. The armature resistance is given 0.2 ohms. So this is the voltage which is given in between the lines. First you have to find out the phase voltage by root 3. This value is divided by the root 3, each value. So we are getting this one. The remaining table is same. Per phase voltage equal to, this is the voltage which is given rated voltage of alternator. So we want to find out the per phase voltage divided by root 3. We are getting the 1100 volts. Next, full load current. So to find the full load current, the rated power of a alternator divided by the root 3 VL, this value. So we are getting the 303 amperes. Here 1000 into 1000, because we are going to convert it into the volt ampere. So the full load current equal to 303 amperes. Definition of the synchronous impedance, it is a ratio between the open circuit voltage to the short circuit current and constant field current. Here 30 amperes of the field current, we know the two values. So take the ratio between these two values, it gives the synchronous impedance. This is nothing but a per phase synchronous impedance, because here we have taken this value as a per phase voltage. Now the no load voltage or the excitation voltage, that is equal to V cos theta plus Ia Ra whole square plus V sin theta plus or minus Ia Xs whole square. The plus for the lagging power factor. In the numerical itself, it is given that we have to calculate the voltage regulation at a lagging power factor. So let us substitute all the values here. So before going to substitute all the values from the synchronous impedance, we have to calculate the per phase synchronous reactance, that is equal to Zs square minus Rs square. All the values we have it, so we can get the value 3.49 ohms. Substitute all the values in this expression. This is nothing but a excitation voltage or no load voltage of a alternator at a full load with a 0.8 power factor lag. So finally you are getting the 1878 volts. Now the voltage regulation equal to E naught minus V by V, E naught minus V by V. Substitute all the values. Here we are getting the 70.72%. Thank you very much. If you have any doubt, you can ask me or you can ask in the comment box of my YouTube channel.